I welcome you all to this course on microscale transport process, to this lecture of microscale transport process. We have been discussing plastic microfluidic devices. We started with microfluidic devices, the manufacturing of microstructure devices, and what we have considered so far is silicon and glass, and we have discussed various techniques to each a channel on that substrate and how to bond another silicon or glass structure, glass wafer on top, so that watertight microstructured device can be fabricated. These we have already discussed. Next, what we are considering is plastic microfluidic devices, and we have discussed various advantages and disadvantages of these plastic devices. In the last class, we talked about various techniques that are employed to make plastic microfluidic devices, and I pointed out that there are primarily three techniques. One is molding, the other is casting, and the third one is micro injection. In case of a molding process, mold is a negative master made of silicon. That is the definition of mold. Mold is a negative master made of silicon and or electrodeposited metal or reticulated polymer. The common method of making a mold is photolithography, and processing at high temperature and pressure. There are other techniques which are employed. Now, molding process means that it is done with a polymer which has a lower melting point. Typically, the temperature is about 70 degrees centigrade, and a Pdms is the common polymer. Now, catalyst plus polymer is poured on a mold and heated. Later, the structure is peeled off the mold, so that the pattern forms. Now, this process here, the polymer in its molten state, that is poured on the mold. That is the idea. Whereas, in case of casting, which I discussed in the last class, a mold or a stamp is pressed into a heated deformable material. That means, here as I said, the common material is PMMA, polymethyl methacrylate, and other plastics are also indicated there. Temperature is close to 170 degrees centigrade and pressure is 10 to 100 bar. So, here the temperature is much higher, pressure is much higher, and the polymer does not go to its liquid state. Rather, polymer is just softened by application of heat and pressure. Polymer is simply softened, and on top on this polymer a stamp or a mold that is pressed, so that negative after cooling and separation, the structure represents negative of mold. So, that you can generate. So, here the polymer is not taken all the way to its molten state, rather polymer is simply softened, so that it can deform at the places where the stamp or the press is put. The other technique that we discussed in the last class is micro injection. Micro injection is meant for serial production on industrial scale. Here the technique is very similar to molding. That means, you are forming a liquid which flows, you are forming the molten polymer which flows into the mold. Okay. In the last class we discussed this technique. Here also it happens in the similar way. However, this is not done on a batch scale, this is done on a serial production. That means, you can produce thousands of them at a time. So, the entire arrangement is more intended towards making it on a bulk scale and for a large scale production, and I have discussed this with picture in the last class how this is accomplished. Now, I would like to quickly summarize the advantages of plastic microfluidic devices. Here the precision is surprisingly high, sub-micrometric precision. See, the way we are talking about, as if we are borrowing a technique which has been there for ages, that you have a negative replica and then you are pouring it or putting the way, I am presenting it as if it is, we are making making an idol out of clay. It's that way, it's that simple. So, the immediate question that comes to our mind is, what would be the precision of this kind of methods? You are talking about a microscale device and you are using a technique which we know already for ages. So, it is surprisingly high. That is why the word surprising is there. What scientists have found out, that this precision is very high. That is one particular aspect here. The other advantage of plastic device is PDMS is transparent. So, I told you what the advantage of transparency is, that you can see what is inside. If you want to make an optical interrogation, that means if you want to put a light source and try to find out how much light is absorbed, how much light is transmitted. So, you can do that, because this structure you can put the receiver or you can put the light source outside the structure, and still you can expect light to pass through the solution that is flowing through the microchannel. So, that is one advantage. The third point is elastomeric quality. I am extremely sorry, this word should be elastomeric quality. Elastomeric quality helps water tightness by holding on tightly to the lead or interconnect. See, the plastic material has some elastomeric quality. I mean, it has some amount of elasticity that we have seen. We have seen in plastic devices that it can, if you pull and it stretches a little bit, which is not possible with glass possibly. So these gives you some amount of water tightness by holding on tightly to the lead or interconnect. That means, suppose you want to put a tube into this device which is made of plastic. So, when you insert it, plastic stretches a little bit and make a space for this device to go in, and when you release, after it goes inside, the plastic material that hugs the tubing such that it becomes somewhat watertight. The idea here is that the elastomeric quality helps in water tightness by holding on tightly to the lead or interconnect. You might have already seen there are while we assemble toys, there is something called a press fit connection. You press it, it shrinks a little bit and it goes in and then fits there. This is called press fit connection, and this press fit connection is possible because of this elastomeric quality of the material. So, that can be utilized here to put some interconnects, put some tubes on this. Weak surface energy helps in peeling from the mold. Yeah, if the surface energy would have been stronger, then the material, after you put it on the mold, then that would have stuck to the mold. You could have gotten it peeled off. So, that is possible because of this weak surface. So, this is a favorable property of a polymer. I mean, this is a property which favors your application. So, that is what you have to keep in mind. The next point is PDMS is permeable to gas. So, trapped air can escape during liquid fill up operation. This PDMS material can permeate a gas. So, if you create a pressure inside the channel, then see, when you start when you start working with your device, suppose you fill the channel with a liquid and the channel is occupying some air. So, what you have to do is either you have to apply vacuum so that air comes out and liquid gets in. Okay, so, you have to make some arrangement to have the liquid penetrate into the channel. Now, this PDMS, I mean, what I learned in places that PDMS is permeable to gas, and so if there is any trapped air inside the channel, when you fill the channel with a liquid for the first time, then this air can permeate out of this PDMS layer, and so liquid fill up operation would be will have less hindrances. The other point is untreated PDMS is hydrophobic. So, PDMS as it is hydrophobic. Hydrophobic means if you want to flow water through a PDMS channel, you will find resistance. If you would have taken an inert channel of that similar size, then in that case you had you find that would be easier for the liquid to flow through the channel, but since it is hydrophobic, so if you want to flow water through that channel, you have to overcome a higher pressure drop. So, that may not be good for your application, or it may be good for your application, you never know, it depends on what application you choose. However, this PDMS can be made hydrophilic after oxidation of methyl group at the surface by oxygen plasma. So, a common method is that you take the PDMS material and put this to a plasma asher, put this in a plasma chamber and use oxygen plasma to treat the surface. So, the oxidation takes place with the methyl group at the surface and PDMS becomes hydrophilic. So, these kind of changes in property, this kind of property change that cannot be implemented in It may not be very easy for silicon and other materials, but plastic has this property. You can change the property of a plastic material very easily by such surface treatment. So, that is one major advantage of plastic devices. So, these are some of the advantages that I have listed here. Of course, nothing comes free. There are disadvantages of plastic devices. One major thing is aging. Plastic devices that will not remain, that will not retain the properties for a long time. So, it has a shelf life. I mean, you make a microstructure device and keep it in shelf. Okay. So, just like when we purchase a medicine, it says okay, 3 years from manufacturing there is a shelf life given. Similarly, for plastic devices, it will not be there for ages. It will not be there for years. So, there is a shelf life. So, that has to be tagged. And the other issue is deformability for high aspect ratio. This I said, I mean, one advantage you get is elastomeric quality, that it can stretch, it can bend, but the same thing would be a disadvantage when you are working with high aspect ratio. High aspect ratio means you have a, suppose you have a hole in a micro channel, the hole is, or suppose you have a channel in a plastic device. So, basically in a plastic plate you have a channel, the dimensions of the channel are such that the aperture there is of the order of micrometer, whereas the depth of that channel is very high. So, that the aspect ratio is almost 30:1. If the 30 is the depth, 1 is the aperture. So, in that case there is a possibility that this may bend when it is under pressure. So, you cannot retain the structure as it is. If you call it a rectangular slit, this rectangular slit will not remain rectangular everywhere. That problem was not there with silicon. So, this deformability is one concern for high aspect ratio, of course, but if you are working with a normal channel dimensions, that is not a problem. The other point is PDMS cannot tolerate high temperature. I said at the very outset, PDMS was used for molding, and molding was done at 70 degrees centigrade. So, at 70 degrees centigrade, PDMS is all liquid and you are pouring it on the mold. So, at 70 degrees centigrade, PDMS is all liquid. So, if you have a PDMS microfluidic device, you raise the temperature to 70 degrees centigrade, you find it is all liquid. It is no longer a structure. So, if you want to have evaporative deposition of metallic electrodes, we have discussed about this thermal evaporation. You remember what we had in the last class? We have discussed about the deposition. We have talked about thermal evaporation in a previous class. Thermal evaporation, where material to be deposited faces the target in a container. This comes under physical paper deposition. We discussed about two types of deposition, physical paper deposition and chemical paper deposition. And under physical paper deposition, we said we can have thermal evaporation or we can have sputtering. In case of thermal evaporation, you apply heat and sublimate the solid material, and against the solid material you hold the substrate or hold the portions of the substrate which is to be where the deposition has to be made. So, other portions are masked, other portions deposition will not take place, only the portion where you want it to be, you are holding that substrate facing to the solid material and you are applying heat, so that the solid material sublimes. Okay. With sublimation, the vapor gets generated and you have a thermal environment which has a gradient. That means, it is hot on this side, so solid is forming gas, but as it travels, as the gas travels downstream over the substrate material, there is a thermal gradient and the gas cools down, and the moment gas cools down, it forms a deposition, right. So, if somebody wants to make a deposition to make an electrode at one particular portion on the channel wall, so he has to resort to either thermal evaporation or the other technique is sputtering. Sputtering means instead of heat, you would be using plasma. That means, you are providing the energy in the form of electron volt. So, these are the techniques that we deposited that we talked about regarding deposition. Now, when we want to do this on PDMS, this evaporative deposition of metallic electrodes is not possible. It is very simple, 70 degree, below 70 degrees centigrade, nothing will sublimate. If that would have sublimated, then that would have that metal does not have any purpose to me. However, hybrid structure made of PDMS layer placed on silicon wafer with evaporated electrode is possible. That means, you can have a hybrid structure, that means this structure is comprising of both silicon and PDMS, so that you can take the benefit of both the technique, both the substrates. Silicon gives you the robustness, silicon gives you silicon helps you in doing the deposition of electrode material or whatever you want. On the other hand, you need some plastic device. You need the properties of a plastic device, for example, surface property, hydrophilic, hydrophobic, that orientations and etc. So, that can be arranged by using the PDMS layer. So, first you take the silicon wafer, change it to change this. First you take the silicon wafer, put the evaporated electrode, and then you go to first you put the silicon wafer, take this to the evaporative electrode, you evaporate the electrode and put it there, and then you go for this application of this PDMS layer on silicon wafer, such that you have the such that you have the benefit of both the structures. That means, you have the evaporative deposition of the electrode taking place. At the same time, you have the structure, the robustness of the silicon wafer. The next technique is direct micromachining of plastics. Here what you have is that you have a technique called microstereolithography, and the other technique is laser ablation. So, instead of applying the mold, instead of using a mold that is a negative replica, you can do it directly. What you do here is you are using a photosensitive resist. This photosensitive resist that is polymerized layer after layer by applying a spot of UV laser. What this technique is, you have a photosensitive resist, then you build the structure from bottom to top. That means, you take photosensitive resist, then you have to create a channel. Channel means a portion that does not have any solid, and around that portion you have a buildup of solid. That is how you can create a channel. Suppose you think of making a channel in sand or in clay. So, you apply you put clay layer one after the other. Now, if we go back to the slide, what we see is that there could be photosensitive resists that can be polymerized by using a spot of laser. That means, you have a polymer, you have the resist which will form a solid structure if you apply a laser light. So, if you apply the laser light only on those portions where you want that build up to take place. Okay. So, basically you have first you have this polymer layer, and you are putting the laser light in selected places where you want the solid to build up. Okay. So, you have a mask on top, so that light will go only through the portions where you want it to be. Okay. So, and so those portions, this polymer is getting solidified. So, one layer develops, then another layer, then another layer, and it continues to grow. And when it is all grown up, then you see, then in between two layers there is the channel that you want. So, it is a completely different type of approach. It is different from the casting or molding that we have talked about. It does not have any replica. it will have a mask and it will have a laser light which will ensure that polymer material solidifies. So, microstereolithography, here photosensitive resists are polymerized layer after layer by applying a spot of UV laser. The other technique is laser ablation. Instead of building the plastic layer by layer, you can destroy the plastic layer by layer in selected portions using the laser beam. So, plastic is removed locally by sublimation of intense laser beam. That means, you are applying the laser beam which is cutting the portions of a solid polymer structure such that a channel forms. So, it is just opposite of microstereolithography. In one case, the sides of the channel is built layer by layer, and here the solid structure is already there and you are cutting channels using laser. So, these are some direct micromachining techniques that are available. However, these techniques are not that widely used. I mean, the techniques that are most widely used is hot embossing or casting or molding or micro injection. These are the techniques which are more popular. However, these microstereolithography or laser ablation, these are some of the techniques that are available. Once you have done once you have made the channel the way you want, it could be a circular channel or it could be a rectangular channel. Once you have the channel the way you want it, then you have to put a lead on top and then go for a direct bonding, or then go for a bonding, right. So, that is exactly what we have done previously with silicon, you remember, and then we talked about two types of bonding. One is anodic bonding and the other is fusion bonding, right. So, here in this case what we have is we have a bonding of two wafers. There are two types of bonding we discuss here. One is direct bonding and the other is adhesive bonding. There are of course, some other types of bondings available. One is eutectic bonding, and this is the eutectic bonding. So, there are practically three types of bonding. One is direct bonding, the other is adhesive bonding, and the third one is eutectic bonding. The adhesive bonding is very popular, and direct bonding is also used. Now, direct bonding refers to bonding between substrates of same material, so that no problem of thermal stress from mismatch of expansion coefficient happens. Here the bonding is done between silicon and silicon, or glass to glass, or polymer to polymer, right. That is, earlier we talked about silicon to glass. You remember, we said that glass has, when you apply a voltage between a glass and a silicon, the sodium ions, they penetrate into the silicon layer and it has a very watertight bonding, it develops a very watertight bonding. Now, here there when we talked about this glass and silicon bonding, this thermal stress came into picture, because for anodic bonding we had a temperature of 400 degree centigrade. I mean, even if you apply a voltage, still you have to take this system to a temperature of 400 degree centigrade. There this question of thermal stresses came in to, we discussed about this thermal stress. We talked about the differing expansion coefficient, one the expansion coefficient of silicon and the other is the expansion coefficient of glass. Okay, and if the expansion coefficients are widely different, and when you are raising the temperature to 400 degree centigrade, it is likely that this material will tend to bend, because thermal stresses will develop. One tries to, you are trying to bond two layers. Okay, now one layer tends to expand more, the other layer tends to expand less. So, there would be a mismatch. Now, when you are going for a direct bonding, that problem does not exist, because here the bonding is between substrates of same material, silicon to silicon, glass to glass, or polymer to polymer. That is what we are referring to. So, no problem of thermal stress from mismatch of expansion coefficient. The other type, I mean, how we get into this direct bonding, I will discuss this in a moment. Next is adhesive bonding. Adhesive bonding, here you can use a glass layer sprayed, screen printed or sputtered on silicon. Annealing the stack at sealing temperature makes the glass layer to melt and flow. Upon cooling, a strong bond develops. So, that means you have two layers, in between you put some glass. How do you do that? A thin glass layer, either you screen print it, that means you put, just like we have an inkjet printer, you know it's a similar way, because you need a very thin layer, because that glass will melt and just create the bond. Okay. Or it could be sprayed or sputtered. Sputtered means you are going for a physical vapor deposition. So, either way it can be done, and it can be put on the silicon wafer, and then you are putting one against the other and you are going for a fusion bonding practically. You are raising the temperature so that the glass melts and it flows. Okay. Upon cooling, a strong bond develops. The other type of adhesive bonding is use of epoxies or UV curable epoxies and photoresists as glue. These has advantage of low process temperature and can be applied to all kinds of substrate material. Yes, these epoxies are very popular. If you need to bond two layers, these epoxies can hold a significant amount of pressure, and these are cheap, it is readily available. Epoxies are common material that we use to put fixtures. I mean, the kids use to make those work education type drawings and all structures. So, you can use these epoxies, those are very popular. So, epoxies, UV curable epoxies and photoresists as glue has advantage of low process temperature and can be applied to all kinds of substrate material. Let me point out that there exists another technique which goes by the name Eutectic bonding. Not that it is a very general one, but just look at the technique here. A thin gold film is sputtered on silicon wafer. Gold silicon eutectic bonding is achieved at a relatively low temperature of 360 degrees centigrade. Do you know what a eutectic mixture is? You got to go and read what a eutectic mixture is. Gold and silicon, it forms a eutectic mixture. That means it does not. So, when it comes to melting of this material, it follows a different temperature. So, you got to, sorry, it becomes a single phase. So, so this eutectic mixture, it has its unique properties. So, gold silicon, it forms a eutectic mixture, and that so if it becomes a single phase, then that is basically the bonding is, it is practically it is the single. So, it is like any direct bonding if it forms a single phase. So, now, you remember when we talked about this anodic bonding with glass silicon, there even the temperature was 400 degrees centigrade. Okay. If somebody wants to make a silicon direct bonding, the temperature should be around 1000 degrees centigrade. So, these temperature levels are pretty high. That way, if you use the gold silicon eutectic, if you apply a gold layer between two silicon layer, since gold forms a eutectic mixture with silicon and it will follow a different temperature, it will not melt at the temperature silicon dictates, it is not that way. So, you can take advantage of that and get this bonding done at relatively low temperature, 363 degrees centigrade. Protocol for silicon direct bonding. Now, we have talked about three types of bonding. One is direct bonding, the second one is adhesive bonding, and the third one is eutectic bonding. Now, direct bonding, I said at the very outset that direct bonding can be done between silicon to silicon, glass to glass, or polymer to polymer. Now, silicon direct bonding, that there you have to follow certain protocol. Protocol is something which I tried to summarize here. Hydration of silicon wafer by immersing in hydrogen peroxide H2SO4 mixture, or boiling HNO3 or diluted H2SO4. So, it has some you have to treat this silicon material first by dipping it into certain liquid, and then the bonding between a silicon and a silicon layer takes place at elevated temperature of 300 degree centigrade to 1000 degree centigrade. Next, the annealing is done at 800 degree centigrade to 1100 degree centigrade to improve bond quality. That means, first the bonding takes place at a temperature between 300 to 1000 degree centigrade, and then after that you go for another step, which is annealing, that is done at a little higher temperature, so that the bond quality is improved. It is the technique is nothing. The technique is basically you take the two layers, heat them, so that the silicon melts at the interface and it bonds. Okay, but before that you have to treat the surface, dip it in certain liquid. So, there are certain protocol you have to follow. Temperature also, first you initiate the bonding and then you anneal it, so that the bonding that you have developed, it gets finalized. I mean that so you have to go through certain steps, that is all, but it is nothing, just heating the two layers, so that at the interface the solid melts and forms a single phase. Similarly, for glass direct bonding, we discussed about silicon direct bonding. For glass direct bonding, cleaning of glass wafer with a solution I mentioned here, H2O ammonia, H2O2, and then removal of moisture at 130 degree centigrade. First, that has to be put in an oven, so that the moisture gets so that you get rid of the moisture, and then the thermal bonding takes place by putting these two glass layers, one against the other at 600 degree centigrade for 6 to 8 hours. So, it is a very straightforward protocol. Take the two layers, first make sure that the surface is properly treated by dipping it in certain liquids, and then put it in the oven furnace at certain temperature. You have to hold it for certain amount of time, the bonding will be over. Now, if we go for a metal direct bonding, we talked about silicon direct bonding, we had certain temperature. Here for glass, I see the temperature is less, 600 degree centigrade. If you go for a metal direct bonding, use of high pressure and temperature for 4 hours. Of course, it depends on what type of metal you use. I think it is this temperature that they are referring here, possibly it is iron or steel or some material. So, from material to material it will differ, but it would be at a higher temperature than glass, that is for sure, and you have to apply pressure. Similarly, there could be polymer direct bonding. For polymers with low surface energy such as PDMS, use of surface treatment with oxygen plasma is necessary. So, for polymer direct bonding, if you put the two polymer layers and heat it, definitely there would be the polymer at the interface will melt and you have polymer direct bonding. However, because of this low surface energy of PDMS that we discussed before, that because of this low surface energy, you take this advantage by peeling this PDMS layer from the mold. So, that same problem, this low surface energy, that can be improved by treating this PDMS layer in oxygen plasma. Put it in plasma asher and use oxygen plasma, so that the surface is treated, and then you put them together. In fact, after you treat the surface, if you just put one layer against the other, you can expect some amount of bonding to take place. So, if one layer is to be bonded against the other, typically you take the layer and take that substrate, put it in plasma asher in oxygen plasma, you treat the surface and then put it on this layer, put the two together, and automatically that will be bonded, because you have given that surface energy. Now, that will take care of it. Fluidic interconnects. It could be, first of all, why we need fluidic interconnects. You have the silicon or glass or plastic structure on which the channels are embedded. On top of that, you put a lead and bonded using so many bonding techniques we have: anodic bonding, direct bonding, using glue, adhesive. So, we have discussed about several methods. So, you have already bonded the other layer, one layer on top of the other. So, now the microstructured device is ready. Now, you can put interconnects, that means the liquid that will flow into this microstructure, that has to have some port through which it will flow, right. So, you have to have some connection, some union, so that it can be there should be some thread arrangement, so that it can go in and the outside world can communicate to this microstructure device. So, you have to ensure that these fluidic interconnects are at least the provisions are there. Now, there are two types of fluidic interconnects possible. One is press fit. Press fit we have already discussed. You have this hole through which this interconnect has to be placed, and while putting it you apply certain force, so that the plastic material around that hole that allows this tube to go in there, and once it goes in it hugs the tube because of this elastomeric quality. So, that is typically what we mean by a press fit arrangement. So, press fit utilizes elastic force of coupling parts to seal fluidic access, okay, and the sealing force is relatively small, suitable for low pressure applications. All right. So, you can arrange a sealing by depending on this elastic force. However, the force is relatively small. So, if you have a high pressure generated within this microstructure, automatically you will see that there is leakage taking place through that port. Got my point? So, that problem is there. So, this press fit arrangements, these are very popular as long as you are working with a low pressure system, because this is more of a just take this and press this in, put little bit of pressure, little bit of force, and the interconnect will go in and seal. However, that it can seal only up to certain pressure. The other method is what you call glued. Glued means adhesives offer good sealing by filling the gap between external tube and the device opening. So, you have an external tube and you have a device opening. That means, you have this device, on top of that you put a lead, okay, and then you etched a hole. If it is a silicon, then you etch using this deep reactive ion etching technique, because that technique will give a hole of high aspect ratio. The other techniques there are problems. So, we discuss this, you make the hole there. Now, in that hole the capillary has to get in. So, and around the capillary you have to apply something such that it becomes there should not be any leakage taking place when you have pressure inside the microstructure device. So, for that we talked about this press fit, and we said that the limitation is that moment you have higher pressure inside this microstructure, inside this device, then automatically liquid will start leaking from that port. In case of glued, you apply adhesives. These adhesives offer good sealing by filling the gap between external tube and the device opening. Surface is roughened for better adhesion. So, on the surface you roughen it. This we have seen. I mean, if you bond a sole on the shoe, that person, the cobbler, he first roughens. He has a typical device by which he roughens the sole and then he applies the adhesive. So, surface roughened for better adhesion, that is understandable. Polymer glue is used between glass capillary and silicon wafer. So, you have a silicon wafer, you have a glass capillary which goes in there, okay. Still you can use polymer glue. At the very outset I said these epoxies and these UV curable, these glues, these are very effective. If somebody is using it for a small scale, I mean if it is a moderate pressure and if he is not fussy about keeping things very pure, these polymer glues are perfect for these applications. So, a press fit and glued, these are the two types of interconnects that you understand. I mean, what the objective here. there is a glass sealing on metal tube which is possible. So, when it comes to silicon and glass, you can use polymer glue, that is the last point, right. You have a silicon wafer and a glass capillary goes in there. Glass capillary is it's easy to make glass capillaries. So, glass capillary is going in there and you can apply the glue around. However, when you have a metal tube, that means here we are working at higher pressure, or here we are working with certain materials for or certain temperatures for which a metal tube would be necessary. So, if you have to use a metal tube, then a common material that is used is called Covert Tube. It is an alloy of nickel, copper and iron, okay. And this tube basically what you do here is you take the tube, okay. You take the tube, suppose this is the cover material, all right. This is the cover material, this is the Covert tube, and then on this basically this is the place where you have, this is the roughened portion, so this is the fluidic access, this is Covert tube, okay. This tube is basically Covert tube, okay. This is silicon substrate, okay. And this is the, so you have suppose now, and then there is another layer here, I am sorry. So, this is the bottom plate, this hatching represents the bottom plate, this hatching represents the top plate, and suppose this is the channel we are referring to. So, the fluid will come through this and will pass through this channel, all right. So, that is the idea. Now, you have to mix, so this portion is roughened etcetera and they go in there. Now, you have to do this bonding, and since this is a metal, okay. So, the common method of doing the bonding is you put small glass beads around this corner, you put glass beads, okay, and then you place a carbon fixture around the joint and anneal the whole thing, anneal the assembly at 1020 degree centigrade. So, you take this entire joint, you put it in a carbon fixture, then you put it in an enclosure and heat this and heat whatever is inside up to a temperature of 1020 degree centigrade. What happens is this glass melts, and this glass helps bonding between these two materials. So, glass sealing on metal tube is possible. So, if somebody has to use a metal tube that to be connected to the silicon wafer, what he will do is he will use small glass beads, and those glass beads are to be heated in a carbon fixture, so that that glass melts, it flows through the nook and cranny of this corner and ensure that the bonding takes place. So, that is the way. There is another popular item that we have here, which goes by the name plastic coupler. Let me draw how this plastic coupler looks. here the tube is inserted through this portion. So, these hatching refers to the coupler. So, this hatching refers to the coupler. So, this is the coupler. So, coupler is basically an annular material. So, this annular material is this one, okay, and the glass tube is inserted. So, this is the glass tube. So, this is the glass tube. Okay, so, glass tube is inserted to this. So, this is the silicon wafer that you have. Now, the idea here is that this coupler material, you apply some heat. This coupler material is made of plastic. This plastic material melts, may not be perfectly melt and leaking from everywhere, it just gets softened, it melts to some extent, and this plastic material flows, and this when it flows through various gaps, the places where the leakage can take place, it will flow through those places and it will make a permanent sealing. So, once you take this, once you put, so you apply the coupler, okay, you apply the coupler, it would be a similar to when we purchase a new pen, we see on the tip of the refill there is something, okay, it would be a very similar one. You put this inside the hole, and then you apply heat, the coupler material melts, it flows through the nook and cranny of that intersection and ensures that this becomes watertight. But once it melts, this coupler material is gone. So, once you take out, then you have to remove that coupler material and you have to put another coupler when you can use it. So, plastic coupler, if I write it, if I see what we have written here, it is basically the coupler is a smaller annular material at the tip of the external capillary that is inserted directly into each opening. Thermal annealing allows the plastic to reflow around the opening. Once cooled, hermetic seal results. Coupler can offer elastic force to some extent. So, you understand how a coupler works here. So, this is a glass tube, and just at the tip of the tube you put a small annular plastic material and insert it, and then apply heat locally, so that material melts. But it melts means if it liquefies and it leaves the place, it is not that way. It softens, it melts somewhat, flows through the nook and cranny of that interface and ensure that this whole thing is watertight. There is a possibility of integrated O-ring, that is also people have looked into. The picture would be something like this. You have what you have is an annular area will be etched first by one of the techniques DRIE say. Deposit an oxide or a nitride layer, deposit an oxide or a nitride layer, silicone rubber will be squeezed into the cavities, fluidic access will be opened from the back side by DRIE, and next oxide or nitride layer is etched in buffered HF acid and SF6 plasma. What this means is, first what you do is you etch an annular area, So, this is the annular area. What is this annular area? You had a silicon wafer, this is the silicon wafer, you etch an annular area, this is that annular area. I should have made it uniform. This looks a little bigger. So, you etch this annular area. So, think of it, this is basically an annular area, all right. This dip, this is the one. See, if you look at the top view, this portion refers to an annular area. Okay. So, this dip, I mean, I just mind it, I mean, it should have been closed here, then it would have been uniform. Okay. So, this portion refers to an annular area. So, this you ensure by doing an etching, you form an annular area. Then on that annular area, you deposit an oxide or nitride layer, SiO2 or Si2N4, you deposit. You know how to do this deposition. You treat this, say for example, when it comes to deposition by SiO2, you keep it in oxygen at a temperature of 600 degree centigrade or so, automatically a SiO2 layer of micrometer type thickness. So, that you can achieve. So, you form a SiO2 layer. On top of that, silicone rubber will be squeezed into the cavities. Here you make a cavity in which you see, since you form this annular layer, when you make this, when you make a coating of SiO2 or Si2N4, automatically this portion will also be dipped like this. Okay. So, when you make this coating of SiO2, Si2N4, automatically these portions will be dipped. So, you have a cavity here, and that cavity will be filled by silicone rubber. So, silicone rubber will be squeezed into this cavity. That means, you make it, you heat it, get it in a molten state, so that you can squeeze it inside that cavity. Silicone, remind it is not silicon, it is silicone, CONE, silicone rubber. So, it is a completely different material. Okay. So, that is squeezed into this cavities. After you do that, then you open a fluidic access from the back side, that means from this side, from the back side means this side. Whatever you are doing is on the top, silicon oxide layer, then the silicone rubber put in there, then you open a fluidic access from the back side. That means, you by DRIE, deep reactive ion etching. So, that means, you cut off this portion, you remove this portion altogether, you etch it out. I mean, you are basically using a dry etching technique to take out this material. So, once you take out this material, what you end up with is, okay, so you etch this material, and then oxide or nitride layer is etched in buffered HF acid and SF6 plasma. That means, you first etching this layer would be easier, because this portion is silicon, mind it, this portion was silicon. So, etching this part would be easier. So, this part would be etched quickly, okay. And then when you try to etch this layer, it would be difficult to etch this layer. This we pointed out, because silicon SiO2 acts as a mask, it is much difficult to etch the SiO2 layer. So, for this you have to bring in the plasma. So, you get this part also etched out. So, once you take this whole layer out, then what you end up with is a structure something similar to this, where the glass tubing runs like this, and this silicone rubber that you put there, that is acting as the seal, that is acting as the seal, you see. So, this is the silicone wafer. So, you put first, you take the silicone wafer, put a layer on top, okay, so that you form a cavity in these places, all right, and pour the silicone rubber, which is different, squeeze it into this, which is going to act as a gasket. So, you put it there, then you go from the back side, first remove the silicone layer. Removing silicone is very easy, it's not at all a problem, but SiO2 is difficult to remove. For that you have to go for dry etching, and which you need to go for a stronger etching technique, and that you do. And then after that, once you remove this whole material, then what you have is you have this fluidic access made, and this silicone rubber is acting as a O-ring. You know what a O-ring is, okay? You need a O-ring which practically acts as a gasket. So, that O-ring would be there. So, this would be acting as a O-ring. So, these you have so what you have is this structure with integrated O-ring. That means, you are not having a separate O-ring which you put and then you put the tube, it is not that way. Instead, what you have is you have the O-ring which is already inbuilt inside the structure, that is what we are referring to, integrated O-ring. In the next class, we will discuss about the biocompatibility issues, probably very briefly what are these biocompatibility issues in microstructure, and then we get into the theories of microfluidics. We will probably start with mixing between two streams. That is the first topic that we take up as far as the theories of microfluidics is concerned. So, next class, very briefly I touch upon the biocompatibility issue, and then we get into the theories. We treat that the discussion that we had so far on microfabrication, that is over.